Hello and welcome back. I'm Matthew Lay, and we are going to continue our study on voltage dividers. In this lesson, we are going to look at a voltage divider that has multiple loads connected to it, and we're also going to have multiple voltages that those loads are dependent upon. So let's get started. We have some objectives. First and only objective is to calculate our resistor values for a multi-loaded voltage divider. Okay, so here is our voltage divider, and we have multiple loads on here, and we have multiple loads at multiple output voltages. So this load right here will be at a higher voltage than this one here, but we have two different loads that this voltage divider is supplying. This particular one, and I do specifically say this multi-loaded voltage divider is still a series parallel circuit. We can tell because this component has total current flowing through it. There are possibilities where it could be a different circuit. It could be a complex combination circuit, and we can get into that more in the future. But in this lesson, we're just going to talk about this particular circuit right here. So because we have multiple voltage outputs, we're going to have multiple drops. So our first R1 is still going to be our drop resistor, but it's going to be the first drop resistor. And R2 is going to be our second drop resistor that is just beneath R1 there. And it exists to drop the voltage even further for this second load. So this voltage here, this resistor, this load is going to be at a higher voltage than that particular load right there, okay? And so that's why we need multiple drop resistors to drop the voltage down multiple times. So RL1 here is our first load. If you notice, the loads are numbered from the inside out, where these are labeled from the top down. Some students get that confused. They think that's load 1 and this is load 2. The loads are numbered from the inside out, and the drop resistors are from top down. Okay. So that's our load 1 there, and then our second load is the outermost or higher voltage load. Okay, so don't get confused when you start filling out your tables. Those need to be of that order. Okay, the inner is 1, the outer is 2, and if there's a third one, it would be even a higher voltage out there. Okay, and then we also have our bleeder resistor that we still need. Okay. First off, we have multiple branches now. So at point A, we have a branch. So Kirchhoff's current law tells us that the current that flows into node or point A here has to equal the current that flows out. So we are going to have a current that flows in, which in this case is going to be total current, and it's going to split because this is a parallel component that some of the current is going to go down towards R2, and some of it is going to go to our load. Okay. Then we're going to have another branch at the end of R2 at point B, and so that current through R2 is going to go through this branch, and that current is going to equal the sum of those two currents. So some of it's going to branch off this way, and some of it's going to branch off that way to go to our first load. Okay. Our bleeder current is still going to be 10% of our total current, but our formula gets changed just slightly in the fact that we have to add up both loads now to get to our total load current, and we want 90% of the current from this power supply to go to our loads, and we only want 10% to go through our bleeder resistor. So we have to add up both of our load resistor currents. So we take the current from load 1 plus the current from load 2, divide that by 9. That just means that 90% is going to be going that way, and 10% will be going through our bleeder resistor then. Okay, let's actually put some numbers to this and just work through a problem. I think that'll help us really visualize this. So here I have a sample where our supply voltage is 28 volts. Our first load, this inner load here, is 20 volts, and then this outer load, this second load, is 24 volts. The first load pulls 750 milliwatts of power, and the second load pulls 950 milliwatts of power. So we're going to use those givens to design appropriate voltage divider. Okay, so the first thing we need to do is figure out our currents. Now we know that the current going through this load resistor is using nothing more than Watt's law. So if we take our power across that load and the voltage we divide into that load, we take the power divided by the voltage and we get the current through that load. If we take the power of the second load and divide it by the voltage of the second load, we get the current through the second load. And then we can figure out our bleeder current. Our bleeder current will be the sum of the two load currents divided by 9, meaning 90% would go through those and leaving us 10% going through our bleeder resistor. So we add those two together, divide by 9, and we get 85.565 milliamps. Now to get total current, all we have to do is add up all three of those currents. So our total current is the two load currents plus our bleeder current, which is 85.648 milliamps. Now if you notice, if I move this over, I get 8.565 milliamps, which is my bleeder current. That's 10% of my total current. Okay, so now let's figure out our current through this resistor 1. We know that we have total current going through there, so we just assign total current to that resistor. This resistor right here is going to have total current minus the current that branched this way. Okay, Kirchhoff's current law says the current flowing through this resistor will equal the current flowing out, or the current flowing into this point will equal the current flowing out. So if we know the current going this way and we know the current coming in, the difference between those two would be the current going through that resistor. Okay, so we're going to take that 85.648 milliamps and we're going to subtract the 39.568 milliamps. And that's going to equal 46.065 milliamps. That's going to be the current that actually is flowing through this resistor, okay? So now we know all the currents, because here's our bleeder resistor, that's current through that one. We know the current through our loads. We know the current through that resistor, which is total current, and we know the current through that resistor. So we have all of our currents put together. Now all we have to do is, the next step is to figure out our voltage drops. Okay, so the voltage drop across R1 is going to be our total voltage minus our load voltage for load 2. Okay, we know that our power source is 28 volts and this load is 24 volts, so we're going to have to dissipate, or we're going to have to drop 4 volts across that resistor. Okay. E sub 2, we know that we have our load voltage of 24 volts here, and we know that we have 20 volts here. Well, the only way that can be accomplished is if we subtract those two. That means we have to drop another 4 volts across here. If that's 24 and this is 20, that means that across here I would have to drop 4 volts. So that E sub 2 is 4 volts, or the voltage drop across resistor 2, or the drop resistor 2, is going to be 4 volts. And then, of course, our voltage across our bleeder resistor is going to be our load voltage for load 1, which is 20 volts. Okay, so now we have all of our voltage drops, and we have all of our currents. We can go ahead and figure out our resistance values to round out our design for this particular circuit. Okay, so R1 this is just using Ohm's triangle, Ohm's law, is E divided by I. We know that I total is going to go through this resistor because there's no other branch before it. And we know the voltage drop is 4 volts. We calculated that on the previous slide. And we get 46.702 ohms for R1. For R2, we get the voltage drop across R2 divided by the current that we previously calculated going through R2, and we get 86.834 ohms. Okay? And then our bleeder resistor is just going to be that voltage drop across our load number 1, which is this in parallel with our bleeder resistor, and divide that by our bleeder current that we calculated previous, and we're going to get 2.335 k ohms. Now, if you remember from the previous lesson, I said that our drop resistors are usually going to be fairly small in ohm value, and our bleeder resistor is going to be fairly large in ohm value, and that proves positive here as well. Okay. So now we know our resistance values of all 3 of our resistors that we need for our voltage divider. Okay. So that rounds out our design of our voltage divider. Of course, we can go ahead and calculate our powers and go ahead and double the power and find the next closest wattage resistor for each one of those to select our wattage. We did that in the previous exercise. I didn't do that in this presentation. But I want to pose another problem to us, and this is another circuit. And our question here is solving this circuit any different from solving the previous circuit? So if we look at this, we added a third load here, but do we need to drop any voltage for that load? That load is actually completely across our power supply. Well, because it's across our power supply, we don't have to concern ourselves with the this actual outer load on our design. So we can actually just cover that up with our finger and say, as far as our design goes, that load resistor is not a part of our design, and we have that same circuit that we had before that we just did on some previous slides. Okay, so whenever you see a circuit like that that doesn't require any voltage drop, do not take any of that load current into account when we calculate our drop values for our bleeders and our 2 drop resistors. So we want to treat this circuit just like we did in the previous slides. This one is still going to be a series parallel design that's just going to have an additional load added onto it. Okay, so let's review. Calculating the resistor values for a multi-load voltage divider are as we did in the previous slides. The first thing you want to do is figure out all of your load currents. Once you get your load currents, you can figure out your bleeder current. Once you get to your bleeder current, you can figure out your total current. Then once you have total current, we can start to figure out our voltage drops. And we can do that by just subtracting our load voltages from either the source voltage or from each other to get to those different drop values. Knowing the currents and the voltages, then we can find our resistance values. So this concludes our additional lesson on multi-load loaded voltage dividers. I hope that was helpful, and we'll see you in the next lesson.